Okay, let's dive right into this explainer, where we're going to unpack the fascinating and surprisingly elegant world of quantitative chemical analysis. I want you to imagine, just for a second, that you're a molecular detective. You're examining a sample, and you don't just need to know who is at the scene of the crime, you need to know exactly how many of them there are. That's the whole essence of what we're tackling today, the external standard method.
Because really, identifying a substance, that's only half the battle. We've got these amazing tools that can tell us exactly what molecules are hanging out in a liquid or a gas. But the real mystery, the puzzle that keeps analytical chemists up at night, is finding out exactly how much of it is actually there. I mean, how on earth do we quantify and measure something so microscopic that we literally cannot see it?
And this isn't just some abstract chemistry puzzle. It has massive real-world stakes. Our source material points out that advanced instrumentation gives us the incredibly low detection limits we need to assure safe foods, drugs, water, and air. Being able to extract the exact quantity of a substance is, quite literally, a matter of public health. We absolutely have to get the numbers right.
Section 1, the quantitative chemistry problem. Let's set up our baseline challenge.
So it helps to draw a clear line in the sand right off the bat. Qualitative analysis is what tells us the identity of a substance. It answers the "what is it?" question. Quantitative analysis, on the other hand, which is our entire focus today, determines the exact amounts. It answers how much. Think of it like this. Qualitative analysis is reading the ingredients list on the back of a cake mix box, while quantitative analysis is knowing the precise, down-to-the-gram recipe the chef actually used.
To get that exact quantity, we need a seriously reliable tool. Today, our playing field is chromatography. By definition, this is a method where a complex mixture is separated into its individual components by flushing it through a stationary phase. Imagine taking a single drop of black ink, putting it on a paper towel, and letting water wick it up. The different colored dyes that make up that black ink are going to travel at different speeds and separate into neat little bands. That fundamental mechanism is exactly what allows us to isolate our target before we measure it.
Section 2, decoding the chromatogram. Let's see how we read the results.
Now, what's really cool is how the physical peaks generated by the instrument directly represent our separated chemical components. As the substances exit or elute from the chromatograph, a detector registers them. Each spike tells us a specific substance just crossed the finish line at a specific retention time. The instrument plots all this data out, effectively turning totally invisible molecules into a clear, readable landscape of peaks and valleys.
All right, so here is the absolute golden rule of interpreting this data. The area under the eluting peak, the actual two-dimensional space inside that drawn spike, is directly proportional to the injected mass of the compound. So a tiny blip, that means there's just a trace amount. A massive mountain, you've got a very high concentration. The physical area literally is the quantity we're looking for.
Section 3, the external standard method. Let's get to the climax of the explainer.
How do we turn that visual area on a computer screen into a hard, trustworthy number? Well, the method is brilliantly elegant. Think of it like using a benchmark weight on a calibrated scale. Step 1, we prepare a reference solution with a known exact concentration. That's our benchmark. Step 2, we inject a very specific volume into the machine, let's call it volume V, and we measure the area of the resulting peak. Step 3, and this is absolutely vital, without changing a single setting on the machine, we inject the identical volume V of our unknown sample. Finally, step 4, we measure the area of that unknown peak. Because we know exactly how the machine reacted to the benchmark, we can totally deduce what the unknown is.
Section 4, doing the math. Let's look at the numbers.
Okay, let's slow things down just a bit, because we need to look at exactly how we calculate this. The crucial point is keeping our variables completely organized. For our reference compound, we already know the concentration, let's call it Cref, and we just measured the peak area, Aref. For our unknown sample, we're trying to find its concentration, Cunc, and we just measured its resulting peak area, Aunc. When you lay it all out, it basically becomes a very straightforward, classic find the missing variable math puzzle.
And this brilliantly illustrates the power of using perfectly identical injection volumes. Because we injected the exact same volume of liquid both times, the ratio of the peak areas perfectly mirrors the ratio of their concentrations. Therefore, the unknown concentration simply equals the unknown area divided by the reference area, all multiplied by the reference concentration. It is incredibly straightforward mathematics, yet wonderfully precise for finding our invisible quantities.
Now, what we just walked through is called a single-point calibration. It relies on a single benchmark and assumes the relationship between concentration and area is a perfectly straight line going right down to zero. It's incredibly fast, and precision is actually increased if your known reference concentration is really close to your unknown. But if you're doing highly rigorous work and want maximum precision, you're going to use multi-level calibration. This involves preparing several different known reference amounts and using a linear regression method to plot a much more precise trend line. It definitely takes more upfront work in the lab, but it creates a much tighter net for catching the exact truth of your sample. And, wonderfully enough, this quantitative method is actually the only one adapted to gaseous samples.
Section 5. Industrial Scale and Automation. How do we take this out of the theoretical and into the real world?
In an industrial lab running thousands of repetitive analyses, this simple external standard method is an absolute workhorse. But it requires strict physical discipline. The chromatograph has to be equipped with auto-samplers, including sample trays and automatic injectors, because, let's face it, humans are simply too prone to error for this level of repetition. The single reference solution has to be periodically re-injected just to compensate for natural baseline drifts. The instrument's mechanical tuning absolutely cannot vary between runs, and above all else, there must be unfailing reproducibility in those injection volumes. If the machine accidentally injects even a tiny fraction of a microdrop more for the sample than it did for the standard, our entire mathematical ratio completely falls apart.
Which brings us to a critical limitation to ponder as we wrap up. The external standard method is truly brilliant for automated, repetitive analysis under perfect, controlled laboratory conditions. But what happens when reality strikes? What happens when our injection volumes aren't perfectly identical, or the instrument stability naturally fluctuates over a long 12-hour run? How do we confidently measure precise quantities then? Well, that is precisely where the internal standard method steps into the spotlight. But we're going to have to leave that fascinating puzzle for another time. Thanks for exploring the Detective's Toolkit with me today.